So I'll talk about something called categorical joins, which is some joint work with Alexander Kuznetsov. So basically the goal of the talk is to explain some relationship between projective geometry of algebraic varieties and derived categories. So let me just some background. So in the talk for variety x, I'll write d of x for the bounded derived category of coherent sheaves on x. So, I mean, one of the main goals of the talk is to say something about the structure of this category, and one way to get your hands on this category is to break it into smaller pieces. So let me just recall sort of the formal definition for how you can break this category into smaller pieces. So the technical notion is, it's called a semi-orthogonal decomposition. Semi-orthogonal decomposition so my notation for such a thing will be dx equals a1, a2, up through an. So this is the notation, and it's a sequence of categories ai inside of dx. So these should be full triangulated subcategories of the derived category of x, such that two conditions hold. So such that the first condition is that oms from f into g vanish whenever f is an object of ai, g is an object of aj, and I is bigger than j. So in other words, what this says is there are no Homs going from the right to the left in this decomposition. And typically there will be Homs in the other direction. That's why it's only called semi-orthogonal. Okay, so this is the first condition. And the second condition is that for every object f in this category dx, there should exist a sequence of morphisms, so which starts at the zero object and it ends up at this original object f, and this sequence of morphisms should have the following property. Let me fit it in here. So the property is that the cone of fi mapping to fi minus 1 should lie in the category ai. Okay, so in words, what does the second condition say? It says that every object has a filtration whose graded pieces lie in these categories ai. Okay, so this is the sense in which this thing is a decomposition of the category. So let me just give you like a few basic examples of this kind of thing that you should keep in mind throughout the talk. Okay, so examples. So the first example is the derived category of projective space. This has a decomposition with n plus 1 terms, so it looks like this. And here maybe just one word about this is that I'm slightly abusing notation. So here, I mean in my definition I said I give you a sequence of categories, here I give you a sequence of objects. This is really just shorthand for the triangulated subcategory generated by O of 1 inside of P of Pn. And I want to point out that this is actually a really simple category. It's just equivalent to the derived category of a point. And the equivalence takes an object of this category, in other words, a complex of vector spaces, to V tensored with O of 1. Okay, and whenever you have an object with this property that's equivalent to the derived category of a point, it's called an exceptional object. And so all these line bundles are exceptional on projective space, and they give you a semi-orthogonal decomposition. So it's easy to see that condition 1 holds. The orthogonality is just the cohomology of line bundles on Pn, and the fact that there's a decomposition is a little bit harder, and it goes back to Baileysm. So that's one sort of fundamental example of this kind of thing. Here's another example, which you should keep in mind. So let's consider Q a quadric in Pn plus 1. so a smooth quadric, and let me assume that the dimension n of the quadric is even. So there's a slight discrepancy depending on whether the dimension is even or odd. Okay, but if you have a quadric of even dimension, then it has a decomposition that looks as follows. So O of 1 is just a pullback of O of 1, and this S here is a spinner bundle on the quadric. And if you don't know what a spinner bundle is, it's actually not so important for what I'll say. It's just some canonical vector bundle in the quadric with the property that if you put it in this sequence, you get a semi-orthogonal decomposition of DQ. And again, all of these objects are actually exceptional objects on the quadric. So the derived category of the quadric is made up of a bunch of copies of D of a point. And I see that I mixed the index up here. It goes up to n minus 1. Okay, but that, again, that's not so important.
And you need only one of the spinners, you don't need both.
Yeah, you only need one of them. That's right. There are two, and you just need one. Okay, so that's the second example. And the last example that I wanted to tell you about is the Grassmannian, is a certain Grassmannian. So we'll look at G25, the Grassmannian of two planes in a 5-dimensional space, and the derived category of this has a decomposition. So let me just tell you some notation first. I'll call U the rank 2 tautological subbundle on this Grassmannian. And then there's a decomposition for the derived category of this Grassmannian that looks like this. So there's O and the dual of U, and then you just twist these 4 times. So then there's O of 1, U dual of 1, all the way up to O of 4, U dual twisted by 4. Okay? So here's one other example. And in all of these bundles are also exceptional, so the derived category of Grassmannian is generated by D of a point. So of course there are many, many examples of semi-orthogonal decompositions, and these are just a few of the simplest ones that you should keep in mind. But one thing I want to emphasize is that if you take an arbitrary variety, its derived category usually won't be built up of a bunch of copies of D of a point. And you can already get examples where that's not true just by intersecting things like this with ample divisors. And so the theory that I want to review for you next is a theory that lets you sort of understand what happens when you take varieties of this form and start intersecting them with hypersurfaces. So that's this theory of homological projective duality. So homological projective duality. From now on, I'll just write HPD for this. So this is a theory that was developed by Sasha Kuznetsov maybe about 10 years ago. This was first developed. And so let me start just by telling you the setup for this theory. So the setup.
The example of the Grassmannian, are the numbers 2 and 5 important, or the obvious generalization works for the Grassmannian?
There are generalizations for other Grassmannians, but then you have to use some Schur functors in place of this. I mean, there is a generalization.
So like for G2n, it will work with no.
I think you need to use symmetric powers here, the tautological.
Even for G2.
I think so. I think for higher G2n. I'm not. I'd have to double check, but I think that's true. There is a generalization for every Grassmannian. Right. So the setup for this general HPD is that I'll start with the variety X, say smooth and proper variety X, with a map to a projective space, and I won't assume that this is an embedding. And the key assumption is that its derived category should have a decomposition that looks as follows. So here, what are these categories AI? They should form a decreasing sequence of full triangulated subcategories inside of dx. And when I write here AI twisted by I, that's just shorthand for the image of this category under the auto equivalence given by tensoring with O of I, where O of I is pulled back to P of V here. So this is the basic setup of HPD. I have a variety mapping to projective space, and I have a decomposition of this form. So let me just point out that all of these examples I told you initially fit into this framework. So, so for instance, in the first example, the map to projective space is just the identity map, and all of these categories, AI, are equal to the category generated by O. Okay? In the second example here, you can take A naught and A1 to be the category generated by S and O, and all the other ones, so A2, A3, etc., just to be generated by this object, single object O. So that satisfies the conditions over there. And for this final example, the Grassmannian maps via the Fluker embedding into a projective space. So that's the map to projective space. And all of these categories, AI, you can take to be generated by O and U. Okay, so all these examples fit into this general setup. And a decomposition of this form, I'll call such a thing a Lefschetz decomposition. And the reason for calling it that is sort of justified by the following line. So here's a, I think I can fit it here.
So what was it? 167. In the case of Grassmannian, all the AIs are the same again, but they're generated by both of them.
Yeah, exactly.
So you don't have to worry about why one factor.
You don't have to worry about, what did you say?
About anything.
About anything, that's right. I mean, they're actually all equal to each other in this case. And yeah, it works. So this category doesn't have to be generated by a single object. It can just be any triangulated subcategory of D of X as long as they form a descending chain. And they should form it, I mean, they also have to form a semi-orthogonal decomposition. Yeah. Okay, so here's the basic lemma about such a decomposition. So let's say I take L inside of V, a linear subspace, say of codimension C. So then I can form the corresponding linear section of X. I'll call it X sub L, so that embeds into X, and I'll call this embedding I. Then the statement of the lemma is that this pullback functor, so I can look at the derived pullback functor from dx to dxl, and I can restrict it to any of these categories appearing in that decomposition. So I can restrict it to, say, ak twisted by k, and I can look at what this functor does when you restrict to xl. And the first statement of the lemma is that this is a fully faithful embedding of ak twisted by k into d of xl, as long as k is bigger than or equal to the codimension c. Okay? So that's the first part of the lemma. And the second part of the lemma says that, so if I look inside the derived category of dxl, what I just told you is that all of these categories embed. So I'm omitting the I upper star. So these categories all embed into the derived category of XL. The second part of this lemma says that these categories remain semi-orthogonal when you embed them into U. Okay? And then the final statement is that you actually have a semi-orthogonal decomposition if you define a category CL to be all the objects F in D of XL, which are orthogonal to all of these categories here. So this should be 0 for every G that lies in one of these twists of AI. Okay? So the lemma says that basically all but the first C of these categories embed into the derived category of the linear section, and you have a semi-orthogonal decomposition just by taking the orthogonal of all of them and calling it this category CL. And the reason that should remind you of Lefschetz, the reason it's called Lefschetz decomposition is it should remind you of the behavior of cohomology undertaking hyperplane sections. Basically, there are some pieces that come from the ambient variety, and then there's some interesting leftover piece in the derived category. So this is sort of the object that we want to understand in HPD, these interesting categories that arise from linear sections. So let me now introduce what's called the HPD category. So sort of the moral of, oh yeah, thanks. The moral of HPD is that these categories CL are actually governed by the case where the codimension is just 1. So let's think about, for a second, the case where little c is 1. So in that case, you can actually do a relative version of this construction as follows. So instead of considering a single hyperplane, I'm going to consider all of the hyperplane sections of X. So to solve the pairs XH like this, so this sits inside of X times P of V dual, where I'm thinking of P of V dual as parameterizing the hyperplanes inside of P of V. So I can look at this total space of hyperplane sections of X, and the derived category of this also has a semi-orthogonal decomposition, which is sort of that, just the relative version of that lemma, and it looks as follows. Category C. So maybe I should just say, what do I mean actually by the symbol here? So this is the triangulated subcategory inside of D of H, generated by box tensor products of objects in here with objects in here. Okay, so you have these categories, they're embedded inside of here, they're semi-orthogonal, and I have this category C, which is their complement. And you should exactly think of this as like a relative version of the previous lemma when the codimension is 1. And this category C is what's called the HPD, homological projective dual to X. And it's an example of what's called a smooth and proper non-commutative variety. There are various ways to make that term precise, but the reason is that it appears as a semi-orthogonal component inside the derived category of a smooth and proper variety. And so in this talk, I'm going to introduce a symbol, which I'll call X dual. And this is just a symbol right now. There's not an actual variety. But I'm going to introduce a symbol X dual such that D of X dual is equal to C. Okay, so basically for the rest of this talk, if you sort of haven't dealt with these non-commutative varieties before, you should just pretend that C is really the derived category of an actual variety X dual. And if you are familiar with sort of non-commutative geometry, you'll see that all I really need to know how to do is base change categories. And the rest of the talk will just make sense even without introducing this symbol. But from now on, I'm really going to use this notation, okay? So I have this category, it's D of X dual, and there's one further piece of structure that this category has. So if you take an object inside of the derived category of this projective space, you can pull it back and then tensor it in this category. And when you do that, you'll preserve all of these components here. And so therefore you preserve C because it's just the orthogonal to those. So what that means is that this category, you can think of that as saying that you have a map from X dual to the dual projective space. So again, just for intuition, if you had an actual variety with an actual map to projective space, then you can take any object here, pull it back, and tensor. And so you get this structure of a module over D of PV dual on the derived category of X dual. And so that's a situation you should keep in mind, but in general, I would just say that this category C is a module over the derived category of P of V dual. But, okay, so maybe just one last time for the rest of the talk, if if you're not so comfortable with that, imagine that we have an actual variety and an actual morphism.
But did you have to specialize to C equals 1?
So this relative thing does work for all C, but as you'll see in a moment, it's really this codimension 1 case actually controls all of those other categories.
Just intuitively?
Well, you'll see. You'll see in the statement of the sort of main theorem in just a second. It's sort of not obvious that it does control the other codimensions. Okay, but before I do that, let me just give you a couple examples of how this category actually works. So I'll actually go through these examples here more or less. Okay, so for the first example, let me just take X to be a linear subspace P of W inside of P of V. Okay? And it turns out in this case that the HPD is really the derived category of an actual variety, and that variety is just the orthogonal to W inside of P of V dual. So by the orthogonal, I just mean the orthogonal under the pairing between V and V dual. Or in other words, this V perp is just the kernel of the restriction map from V dual to W dual. Okay?
So it's the ordinary projective dual.
It's actually the ordinary projective dual, that's right. And again, I mean, that's not sort of obvious from the way I've defined it for you, this category C, but it turns out that there is an equivalence between the derived category of this and the derived category, and this category C that I just defined over there. So that's one example. Another example, let's say X was this quadric, this n-dimensional quadric inside of PV. And again, let me assume that n is even, so we're on the setup that I told you before. Then this category is actually equivalent, again, to the derived category of a variety, and it's equivalent to what I'll call Q star, and this is just the classical projective dual of this variety Q. So in other words, it's the locus of all hyperplanes inside of P of V, such that H is tangent at some point to Q. Okay, and it's just a classical fact that this thing is again a quadric. It's a smooth quadric in the dual projective space. And again, it turns out that this category is actually equivalent to the derived category of this variety. So that's another example. And what about this Grassmannian? So now let's say X is G2. So I need a name for this space. I'll call it U. So U here is just K5, where K is our base field. So this Grassmannian embeds into the Fluker space P of wedge 2 of U. And the dual in this case is actually just the embedding of the dual Grassmannian into wedge 2 of U dual. And so I should point out that this is actually equal to, so this is equal to the classical projective dual of this Grassmannian. Okay, so maybe just a couple comments about these examples. First of all, in all of these cases, this category C is the derived category of a variety, and it's actually the derived category of the ordinary projective dual of the original variety. And that's actually just not true in general. You might guess, oh, it's always the derived category of the projective dual, but typically the projective dual is singular. And this category can never be equivalent to the derived category of a singular variety because it's smooth and proper. So in general, this category C is closely related to projective duality, but it's usually not actually the derived category of a variety, and in particular not the derived category of the projective dual.
But if X happens to be the dual of a smooth variety, then it works?
In all of the known cases,
But it's not obvious that it works.
Yeah, it's not obvious that it works, even if the projective dual happens to be smooth. That's right.
No, I'm saying allow X to be singular.
Allow X to be singular.
Have it do a be smooth.
So in sort of in the whole setup of HPD, you really need to work with a smooth.
You
The
need
input
a
needs
homological lashes decomposition in order to formulate what a homological projective DO is.
So you need X and X to have be smooth.
Yeah,
and not every smooth variety actually has a homological lashes decomposition, so it's
That's right.
I mean, it's not like you just need a map to projective space or just a subvariety in a projective space. You need
You also need,
data.
yeah. And maybe that's worth emphasizing again. In all these examples, I mean, this dual depends on our fixed Lefschetz decomposition that I had from the beginning. But from now on, I'll sort of suppress that. There's always in the background this fixed Lefschetz decomposition in any of our examples. Okay, so this is sort of the basic object. Now let me tell you the main theorem about HPD. So here's the main theorem. So the theorem says that there is a Lefschetz decomposition of this HPD, this HPD category. So I'll call its terms B's, B0, B1 twisted by 1, up through Bn minus 1 twisted by n minus 1. So this can be different than the length of the Lefschetz decomposition of X. So this is a Lefschetz decomposition such that whenever I take a linear subspace L inside of V, and I take its orthogonal inside of V dual, then the following holds. So first of all, I can look at the corresponding linear section of this dual variety X check. And this thing has a decomposition that looks as follows. So here, little l is the dimension of this linear space L, or in other words, it's the codimension of this space here. And so just applying that lemma from before, you automatically get a decomposition like this. And the real main statement is you have a decomposition and you have an equivalence between this category and the category CL that we had for X of L. Okay, so just to summarize in words, what HPD says is that if you start with a variety with a Lefschetz decomposition, there is this HPD such that a linear section of X has a derived category which is closely related to the orthogonal linear section of this HPD. Okay, namely they have two components, they have a component in common. So that's the statement of HPD, and let me just tell you sort of one non-trivial consequence of this. So there are sort of many interesting consequences of it, but here's maybe the easiest non-trivial thing. So let's look at this example that we just did here. So let's take this linear space L to just be a hyperplane. So say the codimension of L is 1, I get a hyperplane inside of here. The orthogonal to that will just be a point in the dual projective space. And so I can look at the derived category of the hyperplane section of X, or the derived category of X dual intersected with a point. So as long as I choose this point generically, the intersection with X dual will be empty, right? Just take it to not lie on this Grassmannian. And in particular, the derived category here will just be 0. On the other hand, for D of XH, just applying the lemma from before, you have a decomposition that looks as follows. So there are 8 exceptional objects. And then there's this leftover category, C sub H. And what the theorem tells you is that this thing is actually 0. This category is 0. So in other words, you find that this hyperplane section is generated by these 8 exceptional objects restricted from the Grassmannian, which isn't obvious beforehand, just knowing that the Grassmannian has a decomposition. So this is sort of one, maybe the simplest non-trivial example of this theorem in action. Okay, and my goal for the rest of the talk is to describe a sort of similar picture with a different classical operation from projective geometry, namely the join of two varieties. Let me move on to that now. Are there any questions about this?
So that was a statement about the section of the dual of the Grassmannish Pfaffian intersected with how many
In this case, in this case, it's intersected with just a point. So it's intersected with the dimension minus one hyperplanes. And all I'm saying is that if you start with a hyperplane in this original Kluger space, it's orthogonal with a point. And so as long as you choose this point to not lie on the dual Grassmannian, then the intersection will be empty. And in particular, the derived category here will be 0. And then what the theorem is telling you is that this extra category just vanishes because it's equal to this. It's equal to something inside of this category, which is 0.
Well, XH is
The hyperplane section of the Grassmannian.
The hyperplane section of the Grassmannian.
the generic, it's a smooth hyperplane section.
Yeah, so what I'm saying is that a generic linear section of the Grassmannian will have a decomposition.
The exceptional collection.
An exceptional collection, yeah.
And you didn't want to drop the first one?
The thing that you lose is, it's sort of from this lemma, the codimension is 1. So remember the decomposition of the whole Grassmannian. The whole Grassmannian was O U dual of 1, U dual of 1, etc. And if the codimension is 1, you exactly lose sort of this first piece. So all of these objects restrict, and then there's potentially something left over as the orthogonal. And what the
So
theorem
you
tells
dropped two of them.
O and U.
You drop O and U dual, yeah. Which is the sort of the first block. It's the first category. Remember the categories were all OU. Yeah, that's right. Good, okay. Okay, so let me now move on to these joints. So eventually we'll see how this theory of joins will allow us, first of all, given two HPD varieties, to produce a new pair of HPD varieties. And second of all, it will allow us to generalize this main theorem. So that's the direction we're headed in, but first I want to sort of just tell you a bit about joins. Okay, so, I mean, just for motivation, let's say that I have two varieties, x1 and x2, sitting inside of P of V1 and P of V2. And let's say there's, say smooth and proper varieties embedded in projective space. Then something that you can do is you can think of them as sitting inside of this bigger projective space, P of V1 plus V2, and inside of this big projective space you can take their join. Okay, so my notation for that will be J of x1, x2, and it's just the union over all points P1 and x1, P2 and x2 of the line, from P1 to P2 inside of this big projective space. So inside of P of V1 plus V2. So this is the join of two varieties. And maybe the very first thing to mention is that typically this thing will be singular. Like, if this, for instance, if x2 is just a point, we're just taking the cone over our variety, which is almost always singular. So this is singular, and that's kind of similar to the way that the projective dual is usually singular. And so it'll be useful to know that there's a canonical resolution of this variety. So let me tell you about that now. I'll call it J tilde of x1, x2. And what is it? So, I mean, we form this variety just by taking the union of these lines in projective space. So we can just take the abstract union of these lines instead. So in other words, we can take this projective bundle, P of x1 times x2, and we projectivize this rank 2 bundle, where here H1 and H2 are the hyperplane classes on V1 and V2. Okay, so this is exactly the abstract union of these lines. It maps to this projective space, and it maps onto our join, and it's a resolution of singularities. And maybe I can just point out, it's easy to see exactly what the exceptional locus of this birational map looks like. So there are only two exceptions. There are two exceptional divisors. I'll call them EK, and they're just given by projectivizing each of the summands here. Okay, so I mean it's just a copy of x1 times x2, and under this map, this thing is contracted onto xk, which sits inside of here. Okay, so this is just some, I mean, right now this is just the two varieties. You always have the join, and you have this canonical resolution of singularity. And now what I want to do.
What's K? What the notation is?
K is just either 1 or 2.
Oh, I see.
Yeah.
Not the field.
Yeah, not the field, yeah, different K. Okay, so now what I want to do is I want to assume that both x1 and x2 are as in the setup of HPD. So I want to assume that they both have Lefschetz decompositions. So let's say for the rest of the talk, we'll be in the following setup. For k is 1 or 2, I'll assume that I have a smooth and proper variety, with a map to a projective space P of dk. Again, it doesn't have to be an embedding. And I'll assume that I have a Lefschetz decomposition. So just to write it out, I have AK0, AK1 twisted by HK, all the way up to AK twisted by MK minus 1, HK. Okay, so it looks a little bit messy, but literally I just assume that for each K I have a Lefschetz decomposition. And so now from this data, I want to construct some smooth and proper category which can be considered something that approximates the joint in the same way that this HPD approximates the projective dual variety. So that's given by the following, I'll call it proposition.
Except that in the usual projective dual case, as you said, the projective dual could be singular, whereas the homological projective dual is a resolution of singularities. Whereas here you have a natural resolution of singularities at the joint.
That's true. I mean, that's true. Although maybe it's not even quite true that the HPD is always a resolution of singularities. It's more that the critical locus of its map of projective space to the dual projective space is the projective dual. And that will turn out to be literally true of this thing that I'll define. Okay, but yeah, so here's the proposition / definition. So there is a P of V1 plus V2 linear semi-orthogonal decomposition of the derived category of this resolved join, which looks as follows. So maybe one thing I should point out to begin with is that the classical join only really makes sense if you're embedded if x1 and x2 are embedded in projective space, but the second row there always makes sense for any x1 and x2. And so this object here is still defined. So this thing has a decomposition which looks as follows. There are sort of a bunch of terms in this decomposition. Let me even move to the next line so I have room. So there will be some terms pushed forward from each of the exceptional divisors. So let me call I sub k this embedding of the exceptional divisor ek. So the first term looks like this. So let me just make sure I don't mess
I
it
sub
in.
k is the one whose image contracts to
xk.
or whose fiber is xk.
E sub k contracts to xk. Yeah. And so there's a decomposition that looks as follows. So let me write it and then I'll sort of explain it. Okay, so in this first row, what have I written? Basically, I've pushed forward from E1, D of x1 box tensor product with each of the terms in the decomposition of x2 except for the very first one. Okay, so you box tensor product with this, then push forward all the way up to the last one. That's what this first row is. And then you do, the symmetric thing from the E2 divisor. And so let me just write what you get. Okay, let me just erase this. Okay, so I just sort of wrote the symmetric thing on this next line here. And the proposition part of what I'm writing here is that, first of all, each of these categories are embedded fully and faithfully by these push-forward functors. Second of all, they form a semi-orthogonal sequence. And actually, it's easy to see that not only are the first and second rows semi-orthogonal, they're just completely orthogonal. There are no harms between the first and second row because E1 and E2...
Because the supports of the two divisors are disjoint.
Exactly, yeah. E1 and E2 are disjoint. So really, I'm just saying that you need to check there are no harms in going backwards along each row. So that's sort of the proposition part. And now once you know that, you can just define as the orthogonal to these categories something which we call the categorical joint. So my notation for it will be, again, it's a non-commutative variety, and I'm going to use this notation where I think of it as D of something. So I'm going to write D of J script x1, x2. Okay? So this thing...
So yeah, it really doesn't matter in which order you write the two rows.
That's right. You can put them in either way. That's right. And so this thing, J of x1, x2, is what's called the categorical joint of x1 and x2. And maybe one other thing which I should explain is what is this PV1 plus V2 linear part. That just means, so this J tilde maps to P of V1 plus V2, and if you take an object here, you pull it back in tensor, the statement is that it preserves all of these components. And in particular, it preserves this category D of J, x1, x2. And in the notation I introduced before, that exactly means that this non-commutative variety has a map to this projective space. Okay, so the categorical joint of something as in the setup, x1 and x2, is a non-commutative variety with a map to the direct sum of projective space of V1 plus V2. Okay, so that's sort of the main object of the talk. Let me just give you a couple examples and then tell you the main theorem about it. Okay, so example 1. So let's take both of these xk to just be a linear subspace of vk. Okay, so first of all, we can consider just the classical joint of x1 and x2, like the first row from over there, and of course that's just the linear span of W1 and W2. Okay? And of course, this is actually a smooth variety, and as you might hope, this categorical joint is really just equal to this classical variety. So in other words, there's an equivalence between this category I just defined and the derived category of P of W1 plus W2. It's not completely obvious, but again, you can check that this is true using the definition I just gave you. Okay, so this is maybe the first example. For a slightly more interesting example, let's look at the following. So I'll take x1 inside of P of V1 to be a smooth quadrant. Again, let's assume the dimension is even, just so we're in the setup that I told you from before. I'll take x2 to be a linear subspace, I'll call it P of k, inside of P of V2. Okay? And again, let's just consider for a second the classical join of these two varieties. So I'll call that classical join Q, the join of x1 and x2. So that sits inside of P of V1 plus K, and that's just a singular, so this is a singular quadric hypersurface, right? So it's a hypersurface inside here whose singular locus is exactly this P of K. And if you want to think of it as, you know, a symmetric pairing, this is the kernel of that pair. So that's why I called it K. So in this case, the classical join is really, you know, it's a singular variety. So it's definitely not going to be true that this categorical join is equivalent to D of Q. So what is it, you might ask? So it turns out that the following is true. So I'll call the proposition. So the proposition is that this categorical join J of x1, x2, it's not equivalent to the derived category of Q, but it's equivalent to the category of modules over a certain sheaf of algebras R. So here R is the sheaf of algebras on Q with the following property. So if you look at this sheaf of algebras and you restrict it to the smooth locus of Q, in other words, you restrict to the complement of P of K, then the sheaf of algebras is actually the endomorphisms of a vector bundle on this smooth locus. And so, like, why am I telling you that? What is the significance? Well, what this says is the following. If you look at this non-commutative variety and you restrict it to the smooth locus, then you're getting the derived category of Q with coefficients in the endomorphisms of a vector bundle, which by Morita theory, that's just the derived category of Q. So what this is telling you is that this categorical join is really sort of only modifying Q along its singular locus. So this is another example that sort of indicates that it is closely related to this, this classical join. Okay, and so maybe now I can tell you the main theorem about these objects, these joins. So here's the theorem. So maybe there are two parts of it. So the first part says that there is a Lefschetz decomposition of this categorical join, x1, x2, and it looks as follows. So here, remember this join lives over this projective space. So H is just denoting the hyperplane class on that projective space. And what I'm saying is that there's a Lefschetz decomposition of this category. So there's a sequence of categories so that its twists give a semi-orthogonal decomposition. And maybe I can just point out that here this length of the decomposition M is actually equal to the sum of the lengths of the original two decompositions. And moreover, this category A naught, I mean, there's some kind of formula for each of these terms in terms of the original categories, but in general, it's complicated. But for A naught, this thing is really equivalent to A10 box tensor product with A20. Okay? So there is a Lefschetz decomposition of this categorical join is the first statement. And the second statement involves its behavior undertaking HPDs. So what I said so far, basically, it says that this categorical join is exactly as in the setup of HPD. It's a non-commutative variety with a map to projective space and the Lefschetz decomposition. So in particular, you can consider the HPD of this thing here. And that will now live over, it will have a map to this dual projective space. There's a second thing which you could do. You could first take the dual, the HPD of x1, the HPD of x2, and then you could take their join. Okay? So if you took their categorical join, then you would have a map to P of V1 dual plus V2 dual. And of course, these two are equal. And the second part of the theorem says that there's an equivalence between these two, which preserves all of the structures. So it commutes with the maps to this projective space, and it identifies the Lefschetz decompositions on each side. So that sort of packs a lot into one statement. Maybe I definitely won't, tell you the proof, but maybe I can just give you some kind of intuition for it, and then do a couple of examples. So here's maybe the way you should think about this statement too. So,
could you just say again, what are the assumptions?
The assumptions are basically just start with x1 and x2 as in the setup. Then you can construct, then this theorem holds. So you can construct this join such that 1 and 2 hold.
So just two projective varieties, each with its own homological Lefschetz decomposition.
What is x1 dual? That's the classical projective dual?
No, that's the HPD. So if K is 1, then I have a variety with the map to projective space and the Lefschetz decomposition. So it's exactly as in the setup of HPD.
So it's a category, or?
So it's a category. It's a non-commutative variety. Yeah, that's right.
So I'm missing what's the join of the two categories?
Yeah. So as I defined everything, and it may look like it depends on having an actual variety, but all of these constructions you can do just with categories, actually. But maybe it's best for me not to explain that right now. We can talk more about it after, but there's sort of a universal construction you can make so that this actually works if x1 and x2 are just categories linear over the derived category of P1 and the
So you can
derived.
define the join of two categories in such a way that
Exactly.
if the categories happen to be the duals of varieties, then it's the join of varieties.
That's right. Yeah, you can. There's a way to sort of make this construction work even if x1 and x2 aren't varieties. That's right.
Thank you.
Yeah, sorry. So everything in the talk you
In fact, to
can.
define the categorical, the join of two categories, you don't really need Lefschetz decompositions. You just need the maps of the projective spaces.
Well, you could define sort of the derived category of the resolved join. Just once you
Right,
have-
that's
Yeah.
what your
Yeah,
position
exactly.
is about.
Yeah, exactly. So you would first define for anything with maps of projective space this resolved join categorically, but then you also need to show that you can break.
Yeah, then you need that.
Yeah, exactly. Oh, right. And so how should you think about this theorem? So let's say that x1 and x2, let's say that we just had subvarieties of P of vk, so k equals 1 and 2. Then you can consider the classical join of x1 and x2, and you can take its classical projective dual. And it's not a very deep result, but this is actually the join of the projective duals of x1 and x2 inside of this dual projective space. Okay? So this is just a statement about subvarieties of projective space, and what I'm saying is that with this definition of a categorical join, this statement actually gets categorified in this theorem.
Where star is
Where star is the classical projective.
projective dual.
Just the classical projective. So this is just a classical statement about geometry, and what I'm saying is that it admits this kind of enhancement to the level of categories. And so maybe I can just briefly tell you sort of a couple of how to use this to say something interesting, just in some particular cases. So the way that you can sort of get something interesting out of that statement is to apply the main theorem of HPD to it. So what would you need to do? You should take this variety, the join, you should intersect it with a linear subspace, and you should intersect the dual with the orthogonal. So let's do that, and let's actually specialize to the case where V1 and V2 are equal, because already then it's quite interesting what you get. So let's assume V1 and V2 are equal, and let me take the linear, sort of the most obvious linear subspace inside of here, just the diagonal, okay? So now I can intersect this join of x1 and x2 with the diagonal. And I can also intersect the HPD with the orthogonal to the diagonal. Okay, so what the main theorem of HPD tells us is the following. So both of these have decompositions that look as follows. So let's say n is the dimension of V. Then there's a decomposition with some of these categories AI, which I just defined, and some interesting piece called CV left over. And on this side, there's a decomposition with a bunch of B categories and some interesting piece, which I'll call CV perp left over. And the statement of HPD is that these two things are equivalent. So in order to get to use the theorem, let's try to unravel what each of these sides are. And I'm going to use the theorem to do that. So since I'm running out of time a little bit, maybe I'll hurry up. So let's think about this left-hand side here for a second. So I'll call it a proposition. So we can look at the derived category of x1, x2 intersected with the diagonal. And the statement is that this is equivalent to the derived category of the fiber product of x1 and x2 over P of V. Okay? And the way you can think about this is that, if you just took the join, maybe I'll just tell you the statement that this categorifies. If I had x1 and x2, which were subvarieties of P of V, and I took their join and intersected them with the diagonal copy of P of V, then it's easy to convince yourself that's just the intersection of x1 and x2. This is x1 intersected with x2. And if you sort of unravel our definition of the categorical join, you'll see that a similar argument proves this equivalence. Okay, but you can just take that for granted. So what I'm saying is that the left-hand side here is just the fiber product of x1 and x2 over P of V. Okay? And so what about the right-hand side? So here, this thing is equivalent by the theorem, the join of x1 dual, x2 dual, and I should take the fiber product with, so what is this V perp? V perp, if you think about it, it's really just the embedding of V dual into V dual plus V dual, given by sending phi to phi minus phi. So it's essentially the diagonal embedding. And so here I'm taking this fiber product, phi of V dual plus V dual. So this is by the theorem you get an equivalence here, and now by the proposition, this is just equivalent to the fiber product of these two over P of V dual. Is that okay? Okay, so now sort of the total upshot of all of this is that I have an equivalence. So I can take the fiber product of x1 and x2, or I can take the fiber product of their duals. And one output of all of this join machinery is this thing which I'll call star, which says that these two fiber products have a semi-orthogonal component in common. So, maybe I'm over time. Maybe I can just say maybe briefly one word about what happens. So, in an example, so
Start with human beings.
do what?
think it started a few minutes late.
Oh, we started a few minutes late. Okay, I'll hurry up in any case. I'll just take like an extra minute. So for one example, let's consider the case where this variety x2 is just a linear subspace. So let's say x2 is P of L inside of P of V. So if you remember from before, the HPD of this guy is just the orthogonal linear space inside of here. And this thing star, which I just told you, it reduces to the usual, to the main HPD theorem for x1 and its dual. Because it's giving you, here x2 is a linear section. I'm taking a linear section of x1 and the orthogonal linear section, and I'm getting an equivalence between these remaining components. So the way you should think of star is it's a nonlinear version of the main theorem of HPD. So that's how you should think of star, and maybe just to give you a taste of what you can say using this sort of nonlinear version of HPD, I can do one last quick example. So let's say I took x1 to be this Grassmannian G25 embedded in P9, and let's say I took x2 to be the same Grassmannian, but then moved by some generic linear automorphism of P9. So in this case, I look at x1 intersect x2 on the one side, and on the other side, I look at the intersection of their duals. Okay? And it turns out that both of these intersections are Claviau threefolds. So remember, the dual is again a Grassmannian of the same type in the dual projective space. So I'm intersecting two G5s here, and the projective duals of them here, and they're both Claviau threefolds. And star actually says that, I mean, you have to unwind things a little bit, but what star says in this case is that there's an equivalence between these two categories. So, and there are sort of many other ways you can try to apply the star, but this is maybe one of the first interesting ones. Okay, so maybe I'll stop here. Thanks a lot.
These intersections, you don't really need them to be transversal, right? You can just take the derived intersections. I mean, it works without any modification.
Yeah, that's right. I sort of suppressed that throughout the book,
but somehow it's all geared up to work without.
It all works if you take derived fiber products everywhere. Yeah.
So you've done many examples.
What?
You have worked out many examples of this. I mean, it's really this comment that it's a nonlinear version of projective duality, homological projective duality. It's really insightful. I mean, that's how we should really think about it. So
yeah.
If you take things for which you know the homological projective dual and you think about them as your x2s, then then you'll get very. So, for example, if you take quadrics or intersections of quadrics and things like that.
You do get something for quad, and in fact, you can even take an arbitrary number of intersections.
Yeah.
You can iterate these joints. You can intersect sort of as many varieties as you want, and then you can intersect their HPDs. So, I mean, I wouldn't say I've exhausted all the examples you get from it, but you certainly get a lot. And also, I mean, the theorem about joint is actually stronger than this because it gives you new HPDs to things. By taking the joint of two varieties and the joint of the duals, you get a new example of HPD pairs. And actually that's useful.
You get new latches and compositions that you couldn't have
that's right.
guessed just by.
So you can sort of take x2 to be the categorical joint of two varieties, and you actually get pretty useful things by doing that too.